Okay, this is a fun topic, I think. We're looking at finding the areas of of regions defined by graphs. And so the first type of at first we've done stuff like this already. So, if I wanted to find this area here, we know how to do that using calculus. We say that, well, I've got my function f. I'm looking from a to b. So the area of this region is the integral from a to b of f dx. So we already know that the definite integral allows us to find area. But we want to expand our understanding so that we can think about more more shapes. So right now, the definite integral only works when we have a curve and we're finding the area down to the x-axis. What our goal is by the end of today, by the end of this video, is to be able to take, some curve function 1 and another curve function 2 and be able to find the area that is contained by those two functions. So that's where we're going. Let's start off with a warm-up problem, though. So take a stab at trying this problem on your own. So pause this video and see if you can make some sense of this and get to an answer. All right, I always think it's pretty helpful to make a graph of what's going on first. So we've got y equals e to the x, and we're looking for the area that's bounded by the x-axis here. The vertical line's x equals ln2, so let's just say this is ln2 and ln4, and then the graph y equals e to the x. So this is the area that we're talking about right in here. Well, because it's bounded by the x-axis and above by y equals e to the x, this is just a straight up definite integral problem. And the idea of these vertical lines, well, those give me my limits. Here's my lower limit. Here's my upper limit. So that area would be the integral from ln2 to ln4 of e to the x dx. All right, well, solving this by hand, we know that the antiderivative of e to the x is e to the x. It's that special function, and we're integrating it from ln2 to ln4. And while ln2 and ln4 might have initially seemed as scary numbers to be your limits of integration, it actually will work out really nicely with our function e to the x. So we have e to the ln4 minus e to the ln2, and we know that e to the ln's cancel off. So this just ends up being 4 minus 2, which equals 2. So that's the area. This is the area of the shaded region. Okay, what about this next graph? It says find the total area enclosed between the graph of this polynomial function and the x-axis from x equals 0 to x equals 2. So before we kind of proceed and just haphazardly start taking the definite integral, it's important that we know the shape of this graph. So we could take this graph, factor out an x, and get x squared minus 3x plus 2. And if we factor this, we get x minus 2, x minus 1. So this is a third degree polynomial. It's got zeros at 0, 1, and 2. So we know that it's going to look something along the lines, something like this. And what we're finding is the area that's enclosed between the graph and the x-axis. So the area that we're finding is this area plus this area. Now, the reason why we need to take caution is that when we integrate, by default, this area is considered positive and this area is considered negative. But if what I'm trying to consider is just the total amount of area that's contained by this graph in the x-axis, I want to be thinking about positive values. In other words, I want to be taking the absolute value. So the expression for my area, then, even though my limits are from 0 to 2, I'm going to split up those limits because I'm going to go from 0 to 1 of my function, and then I'm going to subtract the area from 1 to 2 f dx. Why am I subtracting? Why did I decide to put a negative sign here? Well, I put a negative sign there because this area is negative. So we'll have a minus, which will turn it positive. All right, so let's go through and do that actual work and get to an algebraic solution for this area. Okay, so we have the integral from 0 to 1 of x cubed minus 3x squared plus 2x, and this will equal, and that's dx. Let's actually add them all together. Minus rather, minus the integral from 1 to 2 of the same thing. So we get, when we take the integral, x to the 4th, 1/4, minus x cubed plus x squared from 0 to 1 minus, well, minus the same thing. But this is going from 1 to 2. Okay, so I'm gonna pause this video and go through the algebra solution because you know how to plug in these values. Okay, so if we looked at the left side, when we plug 1 in, we get 1/4 minus 1 plus 1. And when we plug 0 in, it's all x's, so that'll just be 0. So this is the left side. And then minus, so here's the bottom area. If I plug 2 in, 1/4 times 2 to the 4th is 4. Minus 2 cubed is 8, plus 2 squared is 4. And then minus, putting the 1 in, we get 1/4 minus 1 plus 1. Okay, well, this simplifies pretty nicely. It ends up being just 1/4 minus 1/4, which is 1/2. So that's the area of this region that is captured by the function and the x-axis. And this was all done by hand. How would you have done the same problem using the calculator? Well, remember, if we're trying to find the total area and not the net area, in other words, if we want to consider the negative area as being positive, if we want to take the absolute value, the way that you could do this on your calculator is to enter into your y equals the function, but the absolute value of the function. And that'll make all of the area positive. It'll push the whole function above the x-axis. And then we can integrate from 0 to 2. And because I did the absolute value, now I don't need to worry about splitting up my limits. And we get that the answer is 0.5, which is what I would expect. So the whole idea of the nice thing about using your calculator is you don't need to do two different integrals. And the reason is, again, because it bumps up this graph and makes everything positive. All right. Well, now let's move to the kind of the really new ideas. Imagine if we want to find the area that's contained between two graphs. Well, the key thing here is to remember how we started talking about integration. And the idea of the integration is that we're making a bunch of rectangles. So let's draw a little rectangle. And the idea is that that rectangle has an infinitely small width, dx. But what would be the height of this rectangle? Well, the height of the rectangle, from here down, let's add a different color. This height there is just g, and this height here is f. So the height between g and f is going to be, our height is the difference of g minus f. So the area then would be the integral from a to b of our height, g minus f, times our width, dx. Not too hard. Let's look at an example problem of this. Well, first of all, just to be clear, when you're looking at the area of the region between the two curves, like we were doing, it's mandatory that we have the greater function minus the smaller function. So for example, let's say that that's f, and this is g, and say we wanted to find this whole area right here. And let's call this A, B, and C. So that the area, those yellow areas, would be the integral from A to B of f minus g dx, because f is the bigger function here, and f minus g is the height of that little sliver, plus the integral from B to C of, well, now g, in this region, g is the upper function. So g minus f dx. So you need to be very careful to identify which is the upper function and which is the lower function. And if they switch, in this case, f was the upper, now f is the lower. Where they switch, we need to start a new integral. So here we go. It says compute the area of the region between the graphs of f and g. If f is this function right here, and g is that linear function 5 minus 2x. And what we're looking for is that area in between. Okay, so we're going to do this entirely by hand and then check with our calculator. Well, the first part is easy. So the upper function, very clearly is this one. So it's going to be the integral of 4x minus x squared minus 5 minus 2x dx. But what will be my limits of integration? In other words, what are these points? Well, those are the points where my two functions intersect. So the first thing I'm going to need to do is find that intersection. So I'm going to say, well, 4x minus x squared, when does this equal 5 minus 2x? And if we move everything over, we get x squared minus 6x plus 5 equals 0. And factoring that, we see that my limits of integration are 1 and 5, because that's where they intersect. So here's x equals 1, here's x equals 5. So let's do the solution to this on the next page where we have a little bit more room. So we know now that we're looking at the integral from 1 to 5. And simplifying this, you have 4x minus 2x, so 6x minus x squared minus 5 dx. And when we integrate that, we're going to get 6 over 2 x squared minus 1 over 3 x cubed minus 5x, and we're integrating it from 1, or we're evaluating it from 1 to 5. So this equals, well, let's plug those values in, and notice that this is 3. So we're going to get 3 times 5 squared minus 1/3 5 cubed minus 5 times 5, and subtract that with 3 minus 1/3 minus 5. And not wanting to do all this by hand, we can pull up our calculator and evaluate this. So we get, let's see, and I'll pause this. So evaluating those numbers, we get that the area between those two curves is 10.66666, or we recognize that that would be 10 2/3. So just going back, that is this area. We found that this area equals 10 2/3. Well, how could I have done this by calculator? Well, really, once I got to this step, if I had the use of my calculator, and it's important to be able to do both, once you have the use of your calculator, you could just graph this function, 6x minus x squared minus 5, and integrate it from 1 to 5. And when we do that, we're going to get the same answer back, 10.6666. All right, we're going to do one more problem that's all calculator. So it says find the area of the region bounded above by the graphs of f and g of x. So let's put these into our graphing calculator. So the first thing that I'm going to do is find out where they intersect. So I'm going to put in the first function. So I have both these equations put into y1 and y2. I'm going to graph them and see where they intersect. So this graph is a little tricky to see, but I think it'll be easier if we get rid of some of the unnecessary x. So let's look to -15, go down a little bit. Great, so let's find those intersection points. So second calc, intersect, 1, 2, 3. It's going to give me my first intersection point at -0.53. And do that again to find the other intersection point. And we get my other intersection point, which is the x equals 1.31. Okay, so given that, now we can start doing. So we're looking for the area between those two graphs. We find out that they intersected at negative 0.53 and at 1.3. And clearly the top function, this function here, the function that's on top for the whole time is f of x. So what we're going to do is we're going to integrate from negative 0.53 to 1.31 f minus g dx. And how can I compute that quickly on my calculator? Well, being a little bit clever here, what I can do is I can, because you're always trying to save a little bit of time, here's y1 is my f, and then I could just subtract y2. So subtract my y2 value. Oops. And let's turn off this graph. So now we're going to, this is graphing the difference between f and g, and we're going to integrate that using my limits of integration. So we're going from negative 0.53 to 1.31. And this gives me the area between those graphs. And the area is 6.43. And there we go. So the key thing from today's lesson is being able to take two graphs and find the area between them. And the idea is, you're going to have some upper graph and some lower graph, and it's always just the integral of their intersection points of my upper function minus my lower function. Good. There we go.